And welcome back, everybody. So, in the last video, what we were talking about were applications of the singular value decomposition, and this video is going to be part 2 of those applications. So last time we talked about the 2 norm of our matrix of matrices and how it relates to the dominant singular value of that matrix. They are the same. And we also talked about the condition number, where we can try to predict how ill-behaved, how poorly behaved our matrices are when we try to solve them in linear solve against them in linear systems. So what we would like to do now is instead kind of turn our attention toward data reduction or dimension reduction or size reduction in general. We're looking at compression-like algorithms, algorithms that will reduce the total amount of information that we need to store about an object in order to reproduce it. So that leads us to the topic of this video, where we are trying to solidify this idea of what we mean by recovering most of the data. So we want to be able to get a good approximation of our matrices by using as little information about those matrices as possible. This is what allows for a lot of our modern technology to function, right? You wouldn't be able to send a text message without having to compress something, or you wouldn't be able to send media files without having to compress those guys significantly so they can be sent in smaller packets along the internet, along some network. So these kinds of algorithms are kind of at the forefront of compression, right? In data, in particular for statistics, we'll talk about principal component analysis, which is the statistical version of this sort of compression. So in order to really in order to set the stage here, we would like to say exactly what the motivation is. Or we know the motivation, but now we want to figure out how to set this up and see how the singular value decomposition is going to help us to make this reduction. So it tends to be the case that the dominant singular value of a matrix is pretty well behaved. So this dominant singular value is usually fairly large, and it tends to be about on the order of the size of the entries in the matrix. So if your matrix was something like A is going to be like 1, 5, 91, and -3, then you can pretty much bet that sigma 1 is going to be on the order of 10 squared. So it's going to try to follow that 91 and say, okay, I can try to accommodate most, like the size of the elements of the matrix that you're feeding me. So it's really not the dominant eigenvalues that are the problem in this case, and especially it's really the smaller singular values that are really causing the issues, especially when we talk about the condition number, which was sigma 1 over sigma r. And these guys, when we start dividing by very, very small singular values, that condition number blows up. So just like we would in a discrete Fourier transform, or just a Fourier transform in general, we are going to try to denoise the matrix in some sense. We're going to remove the small singular values and pick up what the matrix really is saying out of its largest singular values and its the associated singular vectors. We will also get principal vectors, and these are going to tell us effectively like the general version of what an eigenspace looks like, and it tells us the trend of what the entries in the matrix look like and what they would like to do when you apply this matrix as a multiplication to a vector. So what we're going to do here is we're going to choose some singular value decomposition of A, and there could be quite a few, especially if you repeat singular values, which does happen from time to time. It's not likely, but it does happen. But most of the time, your SVD is going to be unique. But so if you order the singular values in decreasing order, then yes, it's going to be unique. And we'll leave it there. So we're going to go ahead and define a smaller version of this matrix, right? And we're going to just go ahead and call sigma k here the version of sigma that only it's the k by k matrix that encodes the first k singular values of A. And pk we're also going to define as the first k principal vectors, and q to be the first k singular vectors of the matrix A. And once we have that notation solidified, we have the following theorem. And I teased this one way back at the beginning of our Chapter 8 discussion in our review of eigenvalues and eigenvectors. But what we really want out of this section is this low-rank approximation theorem. And we can just read through this real quick. It says that for your singular value decomposition, P times sigma times Q transpose, this guy is going to be of rank R, say, and sigma is going to contain the singular values sigma 1 through sigma R, usual setup for an SVD. We are going to define A sub k using this new notation up here, right? This new stuff up here, to say that we are going to create a new matrix here that only uses the first k important features of each of these P, sigma, and Q matrices, right? The theorem then says that A sub k has rank k, and moreover, that this guy, AK minus A, so the difference between these two matrices is smallest among all rank k matrices that can be compared against A. So in other words, AK here is the rank k matrix that most closely approximates A. So you think about this in terms of like our least squares models, that we are effectively trying to figure out which solutions, well, even though they aren't solutions, which vectors are closest to being solutions to a particular setup or to a particular linear system. And that's essentially what's happening here. We are trying to get the rank k matrix that is closest in the two-norm sense to the original matrix A. And to illustrate this, let me give you a quick example. So remember this very poorly conditioned matrix here. This guy had a really high condition number, and it's due to the fact that sigma 1 and sigma 2 here have a really high ratio against one another. This looks approximately, what, 1/3 times 10 to the minus, or times 10 to the 5th, right, because I'm dividing by that. So approximately that. So this is on the order of maybe 3,000, 30,000? 3,000. 30? 30,000? Yeah, 30,000. Yeah. So the idea being that we really don't want to work with B, but we will sure try if we really must. We're going to get as close to B as we can. So this would be my singular value decomposition that we had before, right? This set of P, sigma, and Q transpose. So these guys are the singular value decomposition from before. And we are going to employ the new notation here, saying that the rank 1 approximation, B sub 1, that I would like to use, just says only use this part, and this part, right? Only break this guy up into the first few components. And what winds up happening here is I still get a 2x2 matrix out of this, right? So this guy is an outer product, and then we wind up dotting that into, or creating another outer product here, so we wind up with a 2x2 matrix rather than scalars. Or sorry, that would be, sorry, this is a scalar, and then these two guys together multiply together to give an outer product. So I do still wind up with a 2x2 matrix at the end of the day. And that matrix, if you run it through MATLAB, you will see that you wind up with this guy. And this guy, even though he's definitely rank 1, I mean, you can see the proportions of these columns to one another. Like these guys, the second column is a multiple of the first. It looked, or at least you can show it. You could show it if you wanted to. But the thing to note here is the difference between these guys. So the difference between B and B1, right? The difference between those guys, and you know what? Let's go ahead and throw some MATLAB in here so you can see how this works exactly when you are doing this for your projects, which are coming up very shortly. So B, what do we say B was? That was, let's bring the notes back up here. Oh wait, no, I don't want to do that. I want this. Yep, there, going. And grab you, pull you out, and there. Voila. Okay, great. 1.0001. Oh, now it's timing out. What gives? Anyway, so what we're going to do, we're going to go ahead and throw this guy into the computer, grab its SVD, and then start pulling apart certain pieces. We're only going to multiply certain pieces of this guy together to get us our B1 approximation. So 1, 2.0001. All right, so here's our matrix, and we can set up, that'll be, oh, what is it going to be? U, S, yeah, S, and then V. And this is going to be SVD of B. Voila. We have our singular value decomposition. So what we're going to create here is B1, and B1 will be the first column, so first column of U, times the first entry in, yeah, this will be a 1, 1. The first entry in S, and then multiplied by, I'm pretty sure it'll be that column of V, but we're transposing it, and we wind up with that. And if I format this a little bit longer, we ask what B1 looks like, and compare that against B. These guys do look very, very similar, but I can ask, what is the rank of B1? Oh, shoot. Typo. There we go. Then MATLAB will tell me that this guy has rank 1, whereas B has rank 2. And more to the point here, what happens if I take the difference between these guys? So this will give me the 2 norm between these two matrices. And we just showed how to compute that last time. It would be a largest singular value out of the difference matrix, or the largest one. And sure enough, in the notes, I've got 9.4869 times 10 to the minus 5. That looks awfully familiar, right? That is actually the smallest singular value that I get out of this matrix. Is that a coincidence? Like hell it is. Let's find out why. So let me go ahead and bring this back to page width, and let's see what happens. There's a specific reason why that happens, and we're going to run through it real quick. Let's see why we wind up with a singular value of B, or for in the general theorem here, why we get the next largest singular value out of that difference. So first, we're going to go ahead and define sigma r tilde, right? And this is going to be, what we're saying tilde because this guy is going to be an r by r matrix. This is going to be a fully sized matrix. We're just trying to pad this with a whole bunch of zeros, and we'll see why in a moment. So use your usual definition for, or use the definition for a sub k. And we are just going to use the first k principal vectors, the first k singular values, and the first k singular vectors of A to produce a sub k. And this, because we're padding with a whole bunch of zeros in this sigma r tilde, we can actually go ahead and add in a whole bunch of zeros so that we don't have to put the k's here on the p and the q. We can just zero out those components. It's exactly what these singular values are, or these zeros are doing for us. They're making it so we don't have to appeal to the smaller versions or the smaller matrices P and Q and sigma K, or PK, sigma K, and QK. We are also going to observe that when we take this difference, the whole reason why we're making this bigger matrix is so we can create this difference between sigma and sigma r tilde. Now, this difference, because sigma and sigma r tilde agree in the first k diagonal entries, we kill those off, right? In that difference, we wind up with, oh, let's see if I did that right. Yep. We wind up with k zeros in the first, oh geez, I did it again. We wind up with k zeros along the diagonal initially, and then we wind up with the remaining singular values. So notice what the biggest one is at the end of that subtraction. Yeah, it's sigma k plus 1. So this is why we see the next singular value after the rank, or the k plus first singular value. So when we actually take the difference between A and AK, we can go ahead and factor out on the left these two factors of P, and factor out on the right these two factors of Q transpose, and what's left in the middle is that difference between sigma and sigma r tilde. So that difference matrix now has a rank of r minus k, right? It is k singular vectors shy of what it was before. And the singular values, even though we haven't listed them in a numerically decreasing order because of these zeros here, we can go ahead and rearrange the matrices P and Q here so that we put the first k vectors of P and Q at the end of the list. So this is almost a singular value decomposition of the difference A minus AK. So these guys are in fact going to be the singular values of this difference, right? And we only have R minus K of them now. So our previous theorem for computing the 2 norm, right? In our previous lecture, we know that because this guy, this is the singular value decomposition or very close to it, and we know what the singular values look like for that difference matrix A minus AK, we can tell you, or I can tell you, that the 2 norm of this difference has to be equal to that largest singular value. So if B is rank K, then this 2 norm, this A minus B, so for some arbitrary matrix B that I can subtract off of A, the 2 norm can't be any larger than sigma sub k plus 1. So we have an upper bound for what these rank K matrices can look like, right? Or what their 2 norm has to be. What we would like to show now is that this difference, this 2 norm, can't be any less than sigma sub k plus 1, right? And that's exactly what we're showing. We're trying to show that the 2 norm is going to give me information about that sigma sub k plus 1 singular value. So what we're going to do, we're going to suppose that some matrix B here has rank K, then the dimension of its kernel is going to be whatever this difference between the number of columns of B is and what its rank is, right? It's the number of free columns that you get in a row echelon form. And we are going to go ahead and create the span of the first k plus 1 singular vectors of A. Why k plus 1? Because we would also like to consider these guys as compared against the kernel of this arbitrary rank K matrix B. So we would like to figure out, or we would like to use vectors that belong to V sub k plus 1, so the span of the first k plus 1 singular vectors of A, and see what happens when we intersect that against the kernel of this arbitrary rank K matrix. Right? So what are the odds that we even have a vector to choose, right? That intersection could be empty. There may not be any vectors that belong to this VK plus 1 span and the kernel of B, right? There's no reason why they should be together or why we should expect there to be any intersection, so we're going to have to show that there is an intersection. Given that the rank of B was equal to K, then the dimension of its kernel, we already noted, is n minus K. And because the singular vectors are orthogonal, and they're non-zero here, they're an orthonormal set, they have to be linearly independent, which means that these Q vectors have to be a spanning, or they're not only a spanning set, they're an independent set of vectors. So the dimension of V sub k plus 1 is k plus 1. So if I sum these two guys together, right, if they had nothing in common, then this sum couldn't be any larger than just the plain old n. But the fact is their sum is n plus 1, which means that there has to be some overlap between these two vector spaces in Rn. So there has to be at least one vector, in fact an entire one-dimensional vector space at least, worth of vectors that live in this intersection. So I do have a vector that is in the span of the first k plus 1 singular vectors of A, and also belongs to the kernel of B. Strange argument, but let me show you where we're going with this. let's choose not just any old vector, but let's choose a unit vector. And this is unit with respect to the standard Euclidean norm, right? We're working with two norms here. So choose a unit vector in that intersection, right? We do get something by the previous argument. There is a u hat that does this. Then I can go ahead and express u hat as a combination of vectors that came from vk plus 1. In particular, I can choose u hat to be a linear combination of the q vectors, right? And that'll be for some collection of coefficients c1 through ck. Because these vectors, q1 through qk plus 1 hat, are an orthonormal set, then I can go ahead and compute the 2 norm of this u hat by simply squaring out each of these cj coefficients and summing them together. This is our general Pythagorean theorem. Got that all the way back from chapter 4, and we're still using it. So not only can I express u hat as a linear combination of the vectors in v sub k plus 1, right, specifically the q vectors, I know what b does to u hat when I multiply b into u hat. So this difference here, a minus b, if I multiply that into u hat, well, that would just be a times u hat minus b times u hat. But b times u hat has to be 0 because u hat is in the kernel of b. So that term drops out. So that guy is gone. It is the 0 vector. So now that I have that, I can go ahead and play the linearity of matrix multiplication, right? I can go ahead and distribute this a into each term of this sum, and then pass the or factor out the scalars cj, and then I remember that a times q is equal to sigma times p. Is that right? That doesn't quite look right to me. I think it would actually be p times sigma. There we go. Yeah. Right, because the scalars have to multiply onto the columns of p rather than the rows. Okay, that makes more sense to me. Not to mention I have to have a p sigma q transpose at the end of the day. But anyway, that's where this last equality comes from. This aq is essentially just doing each one of these a times the q matrix operation, and I'm then going to go ahead and see the same thing on the other side. I'm replacing that multiplication with p times sigma. Okay, so we wind up with this. A minus b can be seen as this particular linear combination that incorporates not only my singular values, but my principal vectors now, pj hat. Okay, great. Pj hat, right? These p1 through p sub k plus 1 are also an orthonormal set. Therefore, I can play the same game with the Pythagorean, the generalized Pythagorean theorem up here, where I can just go ahead and play with the coefficients on the vector, on the linear combination, rather than the norms of the individual vectors that make it up. So if I ask what is the 2 norm of a minus b times u hat squared, well, we just computed that up here. And then I can go ahead and say, well, orthonormal set here, screw it. I can go ahead and just use the coefficients on the linear combination. Now, all of those sigma j's, because of the way we ordered our singular values, sigma j is at least as big as sigma k plus 1, right? As long as j is greater than or equal to sigma or equal to k plus 1, right? And that's the whole idea, that every single one of these sigma j's can be bounded below by a sigma k, or sigma k plus 1 rather. Therefore, I use the same sigma k in each term here, so this would technically be one more step of algebra. Oh, right, wrong color. There's one more step of algebra in here to say that this guy is no bigger than cj squared times sigma k plus 1 squared, and then I can go ahead and factor out the sigma k plus 1 squared from that sum. And again, this sum up here, we already know what its 2 norm is, right? The sum of those coefficients, this is a unit vector, therefore that sum right there is equal to 1. So the thing that I wind up with at the end here is just a sigma k plus 1 squared. So that means that this 2 norm can't be any smaller than k plus 1 or sigma sub k plus 1 either. So we've shown that this 2 norm of a minus b is at least sigma k plus 1 and no greater than sigma k plus 1. So that means that this guy, the 2 norm has to be equal to sigma sub k plus 1. And we're done. That actually shows the theorem here. Right? That's AK already is a vector that satisfies this condition of being of having a 2 norm of sigma sub k plus 1. So among any other rank k matrices, I mean, we've already found a candidate that creates the smallest norm that we can possibly make. So we don't have to use an arbitrary rank k matrix. We can go ahead and just use our singular value decomposition to create one that is probably best suited or most closely related to A. Awesome. There is one tidbit here, one side remark that I need to make, is that this is unique, right? This A sub k matrix that we created is the unique minimizing matrix if and only if sigma k is strictly bigger than sigma k plus 1, right? That means that there's no variability in the choice of eigenvector basis that we get out of A transpose A corresponding to that singular value sigma k plus 1 squared. So the Q transpose matrix can change so that the factorization is not unique, and that's just it's something that you need to be aware of, but usually doesn't show up in practice because that scenario where sigma k and sigma k plus 1 being the same, that does not happen too often, right? In fact, even in like a statistical data set, that is pretty much guaranteed to not happen, right? There's a probability of 0 that is going to happen. But these sorts of scenarios where we get the same singular values are usually what happens when we create mathematical models, and those models have to have certain properties, and sometimes those properties force the singular values to behave in a very particular way, where we might encounter this sort of scenario. But I digress. The main takeaway here is exactly this theorem, that if you were to go ahead and try to approximate your matrix by the best, right, the closest rank k approximation to this matrix A that you could possibly make is related to the singular value decomposition of A, right? And we can actually make it very, very quickly in MATLAB. Okay, cool. So that is about all I wanted to say about this low-rank approximation theorem. What's left to do for us, we only have 1, maybe 2 more videos. I'm going to see if I can't do it in 1 next time. But we are down to our final topic, and that is principal component analysis. So we are going to see this particular theorem be put to use in a contextual format where you can actually see statistically how this guy works and how you might be able to apply this either to your final project or to whatever problem you're working in once you graduate and you are in the workforce and you have some interesting problem that you would like to talk about. So we will talk about that principal component